Oh, what the heck there? Yeah, 3. All right, so I'm going to ask everybody to just type hi in the chat so I know who's here, and we'll go ahead and get started. Let me go over what's happening this week. I did make a change to the assignments this week. So first we have the CER that was due on Monday. That was on electric circuits. So that was on the work that we had done last week. The suggested one, that means it does not count against you if you do not do it. That's Coulomb's law, conceptual questions. That was due on Tuesday. Now this is where the change comes in. I was going to post the inquiry stations. I don't really have enough to make it a good inquiry station assignment yet, so I'm going to wait and see if we can get a few more submissions from other teachers, and then I'll get that to you. But Mr. Kumar had posted a really nice nail lab, so I want you to go ahead and attack that. I posted that this morning, but that's not due until Friday, okay? And then what I've done is delay this electromagnetism CER. That's not due until Monday. We really haven't gotten into the electromagnetism yet, so until you've at least done the nail lab, I think it's premature to be doing this one. So this has been moved to a Monday due date, but we still have the extra credit on Friday. And I'm thinking that what I may do is a video, and then I'll post the link for that video on Earth's magnetic field so that I can give some background information about it. I'm thinking that on Friday I want to go a little deeper into electromagnetism and talk about transformers and power transmission and Faraday's law on Friday. So today I want to somewhat introduce electromagnetism so that you have the idea of magnets. Changing magnetic field induces an electric field. A changing electric field, so that's a current, current is moving, so it's changing at every point in time. So a changing electric field also induces a magnetic field. So one induces the other induces the first. So what electromagnetism video are you supposed to watch for the nail lab? That would be the nail lab video. Okay, it should be when you get over to your assignments, it should be one is the assignment and the next one is the video, but they both say nail lab. One says, I think it says assignment, I'm not sure. The other says video. Okay. I notice there are multiple on your page. There should only be one that says nail lab. There are some electromagnetism links that are posted in the electricity materials. There shouldn't be other links that are posted yet. Okay, so we did say that an electric current produces a magnetic field. A changing magnetic field produces an electric field. So that's the whole idea behind electromagnetism. Now, one thing that I do want to talk about is that if we take a coil of wire, so the wire has surrounding it the magnetic field. So if we go ahead and bend that wire, looking for a good board to do this. If we bend that wire, then we're concentrating those electric fields on the inside of the wire. So if this is our wire, the electric field is, I'm sorry, the magnetic field is going to surround it. Am I getting this in the video? Yeah. Now, if I take that wire and I go ahead and turn it into a loop. So here's my wire. I make a loop. Let's see, we go this way. Yeah. So the magnetic field is piling up on the inside here. You see that these are getting closer, these are further apart. I can't do all of them. That one got too close. But where you have an area where there are more fields, do you think field lines, do you think that that field is going to be stronger or weaker in that place? So yes, indeed, it's going to be stronger where you have the concentration of the field lines, and you can see that they're more concentrated in the center of the coil than they are on the outside. So just by making the wire into a loop, coiling it, we're concentrating that magnetic field on the inside, what's in the center of that coil. So a lot of the things that we do, like with motors, and the nail lab is about wrapping coils of wire around a nail. That's so that we can concentrate the effect that we want to happen. We can concentrate that force. So let me go ahead and talk about maglev. I don't know if you have heard of maglev. I had my maglev device up here the other day. I have it over there. I can go get it. But that technology can be used for things like high-speed trains. Japan was the first to go ahead and have high-speed train. So the idea with maglev, by reducing resistance, whenever you have wire, the longer the wire, the greater the resistance, right? Because the current has to travel along the wire. The further it's traveling, the hotter it gets. So with the idea of using magnets, because you know when you have one magnet pushing against the other, the like poles attract but opposites repel. So in order to do that, they had current carrying wires on the bottom of the train, and then the track, it's not really a track because there's no contact. The track has wires also, and those moving current carrying wires on the bottom of the train induce a current in the ones in the track. Now the problem is, in order to get that zero resistance, the whole idea, remove resistance, and it can go as fast as you want it to go. In order to get that zero resistance, the material on the bottom of the train has to be super, super, super cooled. So in order to do that, I think it's minus 100 and I want to say 180 degrees Celsius that you have to get it to get that zero resistance. And liquid nitrogen is required for that. So the problem with the maglev are really cool. They're really fast. They're really smooth. But the problem is keeping the material that cool. And then once it reaches a certain temperature, if you're not able to keep it that cool, then the material on the bottom of the train becomes ceramic. And typically you can, by cooling it again, get it to have those magnetic properties again, but in time that fails. There's a limit to how many times you can do that. So it's also very expensive to build the tracks for that, but it's a fabulous way of removing resistance to motion. And then you have absolutely no fossil fuels being used to run that train. So that's the idea behind the superconductors and the high-speed trains. Now I want to talk about the right-hand rule. So we said that the magnetic field, a changing magnetic field, induces a current, and a changing electric field induces a magnetic field. So what happens when these two are close to each other? I mean, they have to be close to each other. So what happens when you have the two that are close to each other? So I want to look at this. I did a board over here. And here, this is the idea behind a simple motor. This is the idea behind a simple motor. So we're using a horseshoe magnet. So why would we want to use a horseshoe magnet instead of a bar magnet? So if we have a bar magnet, we have the field lines going from north to south. Whoops, that one's too close. All right, but can you see that you have a concentration of the fields at the end? They're going to be less in here. And really, the field is very weak when you get to the center. But what about if we bend the magnet so that the north and the south are closer to each other, now you're going to have a higher concentration of field lines. So we like to use a horseshoe magnet in order to produce devices that are using that electromagnetism. One of the examples would be a speaker. So one of the CERs is on the speakers. So what happens when you have the current going through certain parts in the speaker, you have the magnet that's bouncing on the cone. You have a paper cone inside your speaker, and that bouncing causes a vibration, and that's what causes the sound. So here is a simple motor, and okay. Anyway, we start with the electric, the voltage. So the voltage supply is from the battery, and there's a wire that is connected to a stable contact. So this part here is not moving, but this armature, this is a coil of wire that's going to be spinning. So this is free to move, whereas these contacts on the ends are not. So from the positive side of the battery, you have a wire that's connecting to a stable contact here, and that brushes against this armature here that has current flowing through it. This has a conductor. And the other side of it is where you have the current flowing back to the negative side of the battery. So we're going from positive to negative. And we talked about convention. That doesn't mean that's the way that the electrons are going, but that's how, according to convention, we talked about current. So that means that your current is flowing through this wire, but now as the wire flips, can you see that the current on this side of the wire should be going that way, but in fact, it's had to flip. And because of that, that changing current in the magnetic field forces it to keep turning. So what we're saying is that the electric field is causing a force. It's causing a current. I'm sorry. The current is causing a magnetic field, and there's also a force that's coming out from that. So if we have the current is going in this direction, and it's going to cause a magnetic field that, let's say it's coming out of the page, so towards you, then the force that is producing would be in the upward direction. So if we just took this horseshoe magnet, we have the magnetic field going from north to south, and let's say we're holding a wire. Let me get another board. Oops. Sorry, I dropped the computer. And it shut down, so I didn't think that I'd be able to get you guys back. So here is a horseshoe magnet. Let me get my book so I'm doing this right. It's 37, 36. Here it is. Let's say this one's south. No, let's not. North, and this is south. Um, so the magnetic field is going from north to south. If we have a wire that we're bringing down within here, within the horseshoe magnet, so let's say it's coming from the back of the board and it's coming out of the page. I don't know if you talked about out of the page. I think that would be geometry that you talk about into and out of the page. Yeah, so this is coming out of the page. We're bringing this down. Let's say the current is coming out of the page. So my finger would point in the direction of the current. My pointer finger is pointing in the direction of the current. This is right hand rule. My fingers are pointing in the direction of the magnetic field, and then my thumb points up. So that means that there is a force that's being created by these two interfering fields, the electric field from the current carrying wire and the magnetic field from the magnet, and that force is in the upward direction. Now, if instead of coming out of the board, the current is going into the board, now I still have to use right hand. It's going to be a lot easier to switch it and do it with your left, but you still have to use your right hand. That's why it's called right hand rule. So my pointer finger has to point in the direction of the current, and these fingers, my index finger, is that index? No, that's my middle finger, has to point from north to south. So in order to make that happen, this is where all the acrobatics come into effect. I have to flip my hand over so that my fingers are pointing from north to south. They're pointing, the index finger is pointing in the direction of the current, and the thumb is pointing down. That means that there's a force on this wire that's going to push it down. All right, so we're not going to have any exercises that you have to do on right hand rule, but I want you to know about it, right? So that you can understand that there are forces that the electric field and the magnetic field are causing because the two of them are interacting, and that's what causes a lot of our electronic devices. We have these devices because we understand these forces that are happening. We have that for our motor. We can get the armature to turn because of that. And let me also mention that a motor, let me get the board for the motor. A motor is taking electric energy. So you're starting with electric energy, like in your car, you have the battery. You get the electric energy from the battery and it makes the wheels turn. So you're starting with electric energy, and what you're getting out of it is mechanical energy. Now, a generator is the reverse of that. So you're starting with mechanical energy. So if I take out the battery, and here I go ahead and manually turn the armature, the coil of wire, then it's going to produce an electric current, and that current you would be able to use to whatever it is that you're generating your electricity for. Maybe you want to have a party outside at night, so you want to have some lights running. So you hook it up to the generator. The generator starts with mechanical energy. Generally, you have to crank it to get it started or something similar to that. And what you get out of that is your electrical energy. So a motor takes electrical energy and turns it into mechanical energy. A generator takes mechanical energy and turns it into electrical energy. So that's about it for today. So thank you very much. Did everybody say hi? I only have 2 highs here, Francis and Gail. I see that there are 3 people here, so I'm missing 1. Anyway, I will see you on Friday, and good luck with the work for the rest of the week. It's really delayed until Monday, most of it. But there is the nail lab, if you can do the nail lab this week. Thank you. I wish I could see you guys. Maybe anybody interested in doing like a online party or anything? I don't know. Let's see. Maybe we can do a Zoom, or I know there are some party companies that you can do parties online, but I don't know. Let me know what you're thinking. All right. Take care. And I'll talk to you again on Friday.